Hi, I'm Mridul, and I'm here to teach the introductory workshop on machine learning. I'd like to stress that all of the claims that I make in this talk and in the workshop apply to basic machine learning techniques. There is a whole world of more sophisticated and advanced methods out there, and some of the limitations and problems that I talk about are things that have been solved in more sophisticated methods. This, however, is geared towards beginners, people who have a bit of a background in statistics and are thinking of dipping their toes into the world of machine learning. So what is machine learning really? Well, it's a surprisingly hard field to define. And so we're just going to call it a set of algorithms for extracting relationships from data, generally with a focus on prediction, which is where it tends to differ a little bit from statistics. But there is a very large overlap with statistics, and it can be conceptualized either as two ends of a gradient, or sometimes with machine learning being a subset of the larger world of statistics. Both of these are defensible positions. However, it's very clear that there is a lot of common ground. In fact, some of the most basic methods that you learn in an introductory class, both of statistics and of machine learning, are the same. You will learn linear regression, you will learn logistic regression, you will learn dimension reduction methods like PCA. Many of the terms that are used in defining these and in explaining these are different, but fundamentally the same concepts apply. So how do statistics and machine learning differ? Well, to overgeneralize a little bit, machine learning as a field grew out of computer science and artificial intelligence, and so has a cultural difference with statistics. Machine learning being associated more with conferences and startup companies, even in the 2000s and 2010s, rather than, say, academic journals and publications. Machine learning methods tend to focus on predictive accuracy. Methods are evaluated based on how well they perform on data. Statistics tends to be more concerned with theoretical foundations and inference, though statistics also does prediction and description. Machine learning also deals with a wider range of input data, images, video, audio, and therefore it has a wider range of applications, as you know. We are not going to be dealing with some of these complex inputs and outputs, but naturally they are a huge reason why machine learning is very important. But I'd like to stress that even though these fields had slightly different origins, there is much that they are learning from each other, and they are moving closer to each other. So where might you, a hypothetical scientist or aspiring scientist with some ability to work with data, but unfamiliar with machine learning, where might you find the methods useful? Well, if you're in the environmental sciences, including limnology, we are now in an era which is data-rich, and we are relatively theory-rich. But because big data in these fields is quite recent, challenging our complex theories with data is still in its infancy. And these methods are well suited to trying to understand how well our theories work in nature. Second, ecosystem models are complex beasts which have dozens to sometimes hundreds of equations. Now, these equations involve relationships that are often chosen for simplicity or convenience, because we don't always have the data that, or historically we have not had the data that allows us to understand those relationships really well. But now, with the increase in data and with techniques like machine learning, we can identify the shapes of these relationships, which means that we can improve the equations that we put into these models and parameterize them. And what do I mean by the shapes of relationships? Well, here's an example from a machine learning model, which was developed as an example, to predict wine quality. And one of its predictors, the percent of alcohol in the wine, turns out not just to be really important, but has this saturating relationship with wine quality. Now, this is not something you need to tell the machine learning model. You do not need to tell it has a saturating relationship or a linear relationship or any other shape. These are things that you can allow the model to learn from the data. And this is where I think machine learning has a lot of power, and in a way that is underappreciated within environmental science. And what the previous slide was just a single dimensional relationship, but interactions between variables, which are also things that we understand relatively poorly, these are things that we can study really well with machine learning as well. What I have illustrated here is a 4-dimensional interaction surface. And I'm not going to go into the details, but what I'd like you to see is that the surface is relatively complex. And also, I did not put in any information that to define how these variables would interact with each other. So these are things we can learn from data. So when might you want to reach beyond your standard toolbox of statistical regressions, for example, for machine learning? Well, from my perspective, the most important criterion is if you do not know enough to specify the equations, that is the functional forms, and the interactions between variables, that is your predictors. This is a very common situation in environmental science, and this is something that is well dealt with in machine learning. But there are some other criteria as well. For example, it's good if you have a fair amount of data. The more, the better. I will stress, though, you frequently hear that you need hundreds of thousands of points to do machine learning. If you are lucky, there are situations in which you can get useful results from hundreds of points. Thousands is better, tens of thousands even more. The more, the better, as always. But don't rule out these methods simply because you have just a few hundred or a few thousand points. Another situation is if you have a lot of predictors or independent variables, and you are trying to deal with things like model selection problems, or you don't know which predictors are worth including. And also, machine learning is not necessarily a very good fit if your main goal is hypothesis testing. It can be used in that manner, but it's a more complex adaptation of the way they work. So why would you not want to use machine learning? And again, I'd like to stress this applies to beginner level methods. Well, one, the power you get from machine learning is from its flexibility in part. But the assumptions and constraints in statistical models, that is their lack of flexibility, also give you a different kind of power. And what I mean by that is by including assumptions and constraints, you can extract a more reliable signal from less data. So when you use a more flexible model, like in machine learning, you pay a cost, and that cost is mostly in the need for more data and better quality data. The output from a machine learning model is much less easy to use than a parameter estimate that you can directly plug into an equation in a dynamic model. It can be used, but it requires more effort. Now, care is always needed when modeling data, but I think it's fair to say that because of the flexibility in machine learning models, it needs more care in thinking through assumptions and model structure, choice of predictions, predictors, and so on. And it can be computationally expensive, though in my experience, even moderately complex Bayesian models can involve a lot more computation. This is all, of course, problem specific. So what are we going to do in this workshop? Well, we are going to hopefully fit your first machine learning models, specifically with regression in mind. That is, to try and predict a continuous variable. We're going to use primarily some tree-based methods, which I have illustrated here on this side. This is a decision tree, which is included in random forests and boosted regression tree methods. And on the right, we have an illustrated neural network, which we will also touch on. I'd appreciate it if you could install the latest versions of R and RStudio beforehand. And we will also have some information about which packages you will use available later on. We will work to visualize and interpret the fitted machine learning models. So we will look not just at these partial effects, which help us understand the shape between that connects two variables, but also how we think about the relative importance of different predictors in machine learning models. And finally, we will talk and work some on evaluating machine learning models through holdout or cross-validation methods which are very powerful and we can port over to statistics as well and benefit from. So in short, this workshop is for you if you're interested but have never fit your own machine learning models. You know the basics of statistical regression methods and terminology. And ideally, you have some experience with R, not that you need to have an expert level of knowledge, because I will share a script, but have some ability to work through a script and understand what it is doing yourself. So with that, I hope you will join me for the workshop. And please bring your questions with you.